Okay, class, so welcome back. So we're going to start kind of a different set of topics. It's stuff that we've seen in the previous lectures are going to come up all the time. But we're really going to start now studying the real numbers in some sense from scratch. Okay, so we're going to try to not just take some of the definitions that I was using before, where we say like, oh, the real numbers are just decimal expansions. We want to understand them as a set, and then as some extra structure that you can put on this set. Okay, and then this is really to gear up to kind of the end of the course where we're going to start studying some analytic properties of the real numbers. So right now, let me just say what we're going to have now. So R is going to be a set with some extra structure. Okay, so what we're going to see is that we're going to kind of keep adding on layers and layers to this set. So this extra structure is going to get larger and larger. And at the end, the goal of this is to say if we're going to add enough structure to this, we're going to determine exactly the real numbers. Okay? So what is like the first extra structure that we're going to talk about? So there's two ways to combine elements of the real numbers. So x, y, in R, and produce a third element z, also in the real numbers. Okay, so these are usually called binary operations. So these are two binary operations, which is just, another word for saying functions that go from R cross R to R. Okay, so a general binary operation on a set is just a function x cross x to x. Okay, so I think you can imagine what they're going to be. So guess what they are. And I'll give it a second for you, and hopefully you will have guessed that one of these binary operations we're going to call plus. So this goes from R cross R to R. It sends xy to x cross y. Okay? And the other one we're going to call dot or multiplication, which goes from R cross R to R again, and it just sends xy to xy. Okay, so I want to just emphasize here that we are doing things from scratch. Okay, so I'm not going to assume that we know anything about multiplication and addition except for some axioms and some properties that I'm going to tell you. And the goal is to kind of assume as minimal amount of information as you can and then derive the rest of these properties about, the real numbers and these operations. So you want to start with as little information as you have and get as much new information from it. Okay, so let me just say some of the axioms for plus. So I'll put it here, I guess. So axioms. So we're just I'm not gonna prove these. These are just, we're assuming that plus and multiplication satisfy these properties. So for the first one, for any two real numbers, a plus b is b plus a, I'll probably say that's going to be addition is commutative. If I take 3 of them, then I can take a plus b plus c, and this is the same as a plus b plus c. So this is commutative. The second one is associative. The other crucial identity or crucial property is that there's an identity for this operation, which means that there's an element, which is 0, so that for all a in R, you have 0 plus a is a plus 0, which is just a. And the other one, of course, is that there's an inverse. Okay, so for every... So this is usually called the identity, just because kind of like the identity function, this doesn't do anything to a. And there's also an inverse, which you think of as also an inverse function. So for every a in R, there exists a negative a in R, so that a plus minus a is minus a plus a, which is 0. Okay? And at this point, again, I'm going to try to emphasize this point. This is a symbol. Okay, so minus a is a symbol. And we're not assuming, we know what the real numbers are. Okay? And in fact, the real numbers are pretty complicated, so, I don't claim to fully understand them. Okay, so I'd like to give you kind of, an idea of how you prove things using these axioms. So let me put a lemma here. So if z and a are in R, and z plus a, oops, sorry, that's not right, and z plus a is equal to a, then z is 0. Okay? So in other words, there's this element of the real numbers which I've identified as the identity. And maybe I'm just going to give these numbers. Where was the last one? Here. Okay. So we have these 4 axioms, and what this is saying is that the 0 element is unique. Okay, so if I have another element of the real numbers which satisfies this property that 0 does, then it is 0. Okay, so here's the proof. It's going to use these axioms. Okay, so I'm just going to write z. We're trying to show that z is 0. Well, I know that z equals z plus 0 by axiom 3. And this is equal to z plus a plus minus a by axiom 4. And this is z plus a plus minus a by axiom 2, by associativity. And now what do we know about z plus a? Well, this is a by assumption, right? By assumption on z. And therefore, this is 0. Okay? So it's something that, of course, we, or at least we assume when we're talking about the real numbers that we can cancel out elements to say that they have to be 0, like that we're subtracting a from both sides. But what we're doing here is proving it without, knowing anything about the real numbers other than these 4 axioms. okay, about addition. So maybe I'll do the multiplication axioms as well. Sorry. Let's see. So multiplication is going to have similar ones. Maybe I'll call these M1, M2, M3, and M4. Okay, so they're very similar, so it's also commutative. So for every AB in A times B is B times A. We have associativity. So for every A, B, C, oh sorry, that should be in R, not A. In R, A times B times C is A times B times C. And then there are different, these axioms are slightly different. So there's again what's called the identity element, which does nothing for multiplication. We know this is the element which I'll denote 1. So there exists some element, which is important here, that this is not the 0 element. So that for every A in R, 1 times A, which is A times 1, is A. And finally, there's also inverses. So for every A in R minus 0, there's a 1 over A. Again, this is not a fraction, because, for example, I don't know how to divide 1 by the square root of 2. But I'm saying there exists some element in the real numbers so that A times 1 over A is 1 over A times A, which is 1. Okay? And maybe I'll provide you another lemma. So maybe, yeah, okay, we'll do this here. Sorry. Okay, so we have a similar lemma to the above. If AB, well, here I have to assume that they're non-zero real numbers. And A times B is B, then A equals 1. Okay, so this is saying the identity element for multiplication is unique. Okay, so maybe I'll just say pause. Try to write down a proof yourself. It's going to be similar in spirit to the one above, but it's a good test to see if we're on the same page. Okay, so I'm going to pause here. Okay, so let me prove this. So it's going to be similar. We're going to write A, and then instead of writing A plus 0, we write A times 1. So this is multiplication 3. Then this is A times B times 1 over B by axiom 4, which is A times B times 1 over B by 2. Then we have, by assumption, we have this is B times 1 over B, and so we can conclude by axiom 4 that A is equal to 1. Okay? So again, something we know, but something we can just show using these properties. Okay? Okay, and finally, finally we have an interaction between plus and multiplication. So plus and multiplication interact in a predictable way. So I'm going to call this property D for distributive. So we have for any A, B, and C and R, A times B plus C is A times B plus A times C. Okay? Oh, and also, I guess I should write one more. If I have b plus c times a, this is b times a plus, c times a. Okay, so it turns out this also has interesting consequences. So this has some interesting consequences. So let me give you the first one. Okay, so the lemma is c times 0 is 0 for every c in R. Okay, so it will follow pretty quickly. All these proofs are reasonably fast. But notice that the axioms that I've given you don't tell you too much about multiplying by a non-zero value. Okay? Because, for the last two we had to assume that there were these things outside of, in the real numbers, but not 0. Okay, but it will turn out that if you multiply anything by 0, you're guaranteed to be 0. Okay? So here's the proof. Well, we know from the previous lemma that z plus a equaling a implies z equals 0 for any a. Okay? And now what you can think of is that this is going to be a very useful way to show that z is 0. Kind of a strange way to put it, but if you want to show something is 0, well, this gives you the equation to solve. You have to find an element of find an element of R where z plus a is a. And hopefully you can choose the element a in a clever way so that you can use some previous axioms. Okay? So here's our goal. So we're going to show that c plus c times 0 is equal to c. Okay? Because this would imply that c times 0 is 0. Okay? So we've kind of made the right choice of element to look at because it's going to relate to the thing that we're interested in. Okay, so let's prove this. Well, we have c plus c times 0. Now, this I claim is equal to c times 1 plus c times 0 by the third multiplication axiom. Okay, so just anytime I see a c, I can replace with a c times 1. And then by distributivity, I get c times, this is equal to c times 1 plus 0 by d. And this is equal to c times 1 by, I guess, A3. So the addition axioms, I'm just going to call A1 through 4 now. And finally, this is equal to c. Okay, by M3. Okay, so I know that I'm being kind of more careful about listing all the axioms than I have been in previous lectures. This is going to be kind of, it's a new kind of flavor for the course where we're going to try to build this real number from scratch. So at the beginning, I'm going to be more pedantic about using all these axioms. And then as we get further into it, you'll see that I just drop using them and mentioning them. Okay? So now, but the main point is that all these kind of wonderful algebraic properties that we're going to learn about for the real numbers of R are going to depend on, so that we take for granted, are consequences of these axioms. So they all depend just on these kind of 9 axioms for the real numbers plus these 2 operations. Okay, so let me mention a couple more things that we can do. Well, we can use the addition function and multiplication operation to define subtraction and division. So we have subtraction, which is just going to be a minus b, is defined to be, okay, just a plus minus b. And division, a over b, is defined to be a times 1 over b when b is not equal to 0. Okay? So you can also use the addition and multiplication axioms, so we can derive plenty of properties of subtraction and division as well. Okay, which formally are just the same exact properties that you get from looking at addition and multiplication. Okay, so let me do 2 more kind of important properties of multiplication. So let's finish with 2 crucial properties of multiplication. So the first one is that this inverse function is unique, or so the inverse element is unique. So if a is not equal, if a is not equal to 0, and b is in R, and we have, a times b is equal to 1, then b must equal 1 over a. Okay? It's going to be, again, kind of a proof by axiom. So again, we start with kind of, with a similar, thing to a trick, if you want to show some of these properties, is that you always start with the thing you want to prove, and of course you want to kind of use the axioms to move you from b to 1 over a, and of course at some point you have to use this assumption that a times b is 1. Okay, so here's kind of how this goes. You can have b, which is 1 times b, by a third axiom. Now that I've introduced a 1, I can say this is 1 over a times b by the fourth multiplication axiom. So sorry, I should probably say this is, be careful with my parentheses. And this is 1 over a times b by associativity. And then this is 1 over a times 1, now by assumption, right, because we're assuming a times b is 1. And finally, this is 1 over a by the identity. Okay, so by M3 again. Okay, so again, you can also see this is the usual trick here is you introduce a 1, and then the last step is going to be getting rid of a 1. Okay? All right, so let me do one more important property. So here's a lemma, which has come up in, I believe, the homework 2 before. So if a times b is 0, then either a is equal to 0, or b is equal to 0. Okay, so let's see the proof. So I claim we can assume a is not 0. Okay? Just because, well, if it was 0, we would be done, right? Then we would have, this would be satisfied. Okay, so we can assume that a is not 0. So therefore, there exists an inverse. So there exists this 1 over a in R, so that 1 over a times a is 1. And of course, this means that 1 over a times b is equal to 1 over a times b, which is equal to 1 times b, which is 1. Oh, sorry, which is b. Okay? So I will, this was associativity. This was identity. And this was, this was inverse. And this was identity. Okay? But now we're assuming, we are assuming a times b is equal to 0, which means that 1 over a times b is equal to 0, right? Because by the previous lemma. But we just showed that this is equal to b. So therefore b is equal to 0. And then we're done, right? So the assumption was if a times b is equal to 0, then either a is 0 or b is 0. We assumed that this one didn't happen and proved that this one had to happen. Okay? So therefore, that lemma holds. Okay, so let me move this up. Okay, so maybe I will just kind of introduce something that we're going to see a little more in the next lecture. But it's going to be essentially the ordering properties of the real numbers. Okay, so of course the real numbers are defined, we know that they have these nice algebraic properties of addition and multiplication. And another crucial thing about them is that we can tell whether, one real number is larger than the other real number. Okay? So again, we're going to see that there's a way to make this kind of formal, just thinking of R as a set with these operations, and the ordering is going to come from a particular subset of the real numbers. Okay, so here's how this goes. So there exists P contained in R, so this is a subset. I'm going to assume it's not empty, called the set of positive real numbers. Okay? So it's going to be we're just going to think of this now as a certain subset which satisfies some properties. Okay? So satisfying the following properties. And of course, these will be properties that are going to be very familiar to you as, as we're thinking of these as the positive numbers. Okay, but again, the moral is we're really going to just think of this as a subset with satisfying these properties, okay, rather than knowing that it's the positive reals. Okay, so the first one is, well, if A and B are in this set P, then A plus B is also in this set P. Okay, so if you add two positives, you get a positive. Same thing for multiplication. So if A, B are is in P, then A times B is in P. And then finally, this is kind of the crucial, or one of the crucial properties. If A is in R, then exactly one of the following happens. Okay, so this is usually, there's going to be three possibilities, so people call this like a trichotomy, to mean, there's three possibilities and one of them has to happen. So the first is that A is in P, okay, that's the positives. The other is that A could be 0, and the last possibility is that negative A is in P. Okay, so these are like the negatives, 0, and the positives. Okay, so if A is in P, we write A is greater than 0. If A is in P union 0, we're going to write, A is greater than or equal to 0, as usual, okay? And again, this is just notation, right? We're not thinking of this as kind of meaning anything at this point. It just tells us that we're in this particular set that we care about, okay? So maybe I'll just tell you the ordering, and then that'll be enough for the day. So here's our definition of saying like one real number is bigger than the other. So take A, B, and R. Then the way you define A being bigger is you just say, well, if A minus B is in this set positives, we're going to write, A is greater than B, or B less than A. And if A minus B is in P union 0, then we write this as A is greater than or equal to B, or B is less than or equal to A. Okay? So let's just give one kind of immediate corollary of property 3. Okay? So this, what it's saying is that A is greater than, A is greater than B, A equals B, or B is greater than A. This is the trichotomy. But if we have, so in particular, if A is greater than or equal to B, and B is greater than or equal to A, this implies A is equal to B. Okay? You can think of this as kind of the R's version of double containment. Right here, for double containment, we were looking at two different sets and saying one of them is contained in, if they're each contained in each other, then they have to be equal. Well, in the real numbers, you're saying if one real number is greater than or equal to 1, and it's also less than or equal to it, then they have to be equal. And it will turn out, again, this is kind of how you usually end up proving that two real numbers are equal. You show that one of them is less than or equal to, or each one is less than or equal to the other. Okay, so maybe I'll write down familiar properties and prove one more lemma and then do this next lecture. So here's some kind of familiar properties. So the first is that A is greater than B, and B is greater than C implies A is greater than C, so we get transitivity. The second is if A is greater than B, then A plus C is greater than B plus C. I think I'm only going to prove the third one of these, so let me just give you kind of hints to show these two. So to prove 2, note that we're looking at a quantity that's of the form a minus, or a plus c minus b plus c, and you want to say that this is positive, and you know that a minus b is positive. Okay, so this is just kind of playing around with associativity, and also the axioms that p is compatible with addition, and that if you add two things you get in p, you stay in p. Okay, and one is similar to that. Again, you're looking at a minus c, and you want to relate it to a minus b and b minus c. Okay, so let me just say a third property, just slightly more involved. So it's that if a is greater than b and c is greater than 0, then CA is greater than CB, and if A is greater than B and C is less than 0, then CA is less than CB. Okay, so let me just finish today by proving this. Well, so again, we're going to write down, we want to write down CA minus CB and hope that that's in P. So maybe I should probably write this as I. Okay. We want to show that this is in P with the assumption that A minus B is in P. Well, we know that this is C times A minus B by distributivity. And let's see, so A minus B is in P, and this is greater than 0, so then by property 2, so compatibility with multiplication, we get that this is in P as well. In P as well. Okay, and for the last part, it's a similar proof, but I'll write it. So CB minus CA, we have to show this is greater than or equal to 0. So this is equal to, again, C times B minus A, where now we know that this is less than 0. Oops, sorry. Yeah, less than 0. And B minus A is less than 0. Okay, so we have to kind of do two things. Maybe one of them I'll leave as an exercise for you. So notice that this is the same as negative C times A minus B. Okay, and this is the thing that I'm going to leave as an exercise for you. Or maybe it will become a lecture problem. So it's going to be show that AB is equal to negative A times negative B. Okay, so notice that A minus B, you can quickly see from associativity that this is the same as the inverse of B, additive inverse of B minus A. Okay, so now this is now greater than 0. This is greater than 0. So this is positive by assumption. Okay, so therefore C by B minus A is positive, so we're done. Okay, so that's all I have for today. So thanks.